Hello everyone, my name is Preeti and this is my third video, Fabric Architecture, in the series titled Implementing Blockchain Using Hyperledger Fabric. Now that we understand the basic terms used in Fabric, let's dig into the architecture. First up, nodes. There are three kinds of nodes that take part in any transaction: client, peer and orderer. Client represents the entity that acts on behalf of the end user. Client create and thereby invoke transactions. Peer, on the other hand, is a node connected within the network and maintains a valid copy of the ledger and global state in it. Every peer has chain code installed on it, and every time ordering service sends some update, it appends it to its own valid copy of ledger and also the modifies the global state. A client must connect to a peer in order to act within the blockchain network, right? And client can connect to anywhere. It's not really bind to one, right? Okay. An orderer is responsible for providing a shared communication channel within the Hyperledger network, and a shared communication channel where the peer, client, and everybody can talk. The ordering service provides delivery guarantee of the broadcasted message. That's the most important thing. Delivery guarantee of broadcasted messages, right? Let's move on to identity management. In the blockchain network, each of the active elements has a digital certificate which determines the digital identity and the permissions of that actor. Now let's understand PKI and its role in Fabric network. A public key infrastructure is a collection of technologies that provide secure communication in a network. There are four key elements in PKI: digital certificate, public and private key, certificate authority, and certificate revocation list. A digital certificate is a document which holds a set of attributes relating to the holder of the certificate. It is used to verify the identity of an actor sending a message. You can view it as a passport of an actor in the network. The certificate authority, or the CA, issues the digital certificate for each actor. Public and private key. Now that we have established how an actor's identity is verified using the digital certificate, how can we be sure that the actor is what it claims to be, and how the message integrity is maintained in a network? It is achieved through digital signatures. Each actor has two sets of keys: public key and private key. Public key is the key which is available at all the participants, and the private key is the key that is unique to a particular actor, right? So, a sender of a message signs the message using its private key, sends it across, and the receiver can use the public key to decrypt the message, right? It's as simple as that. Next, certificate authority. A certificate authority issues the digital certificate to the actors within a network. Any actor who wants to interact must first produce a digital certificate from the CA trusted in the blockchain network. Now there are two kinds of CAs in any network: the root CA, which is the main CA trusted over the world, and the intermediate CA, which has the certificate issued by the by any root CA or any other intermediate CA. So it's like a root CA issues a certificate to an intermediate CA and says, "By the power vested in me, I now pronounce you a CA, and now you can build your own chain of trust and issue the certificate to others in need." Right? Next, certificate revocation list. It is a list of references within a network about the certificates which are no longer valid and should not be trusted anymore, which have been revoked, right? So any actor wanting to verify the identity of another actor must first go through the certificate revocation list and see whether that certificate has been actually revoked. Now it might not always be that a certificate is revoked only because some user is, or some actor is malicious. There can be multiple reasons, right? So it's very simple. Alright, now that some of the basics are clear, let's actually look into a real life example and how we can solve that real life problem using blockchain. As a software developer, I'm sure you must have participated in the requirement gathering phase and created or modified a specification document of what the end product should look like. There are two there are not just two actually, there are multiple people involved in the review process, whether it is the customer, the architect, the developer, quality engineer, product manager, and other stakeholders. So many people. How do you manage the review process? Do you create a specification document and share it through mail, and then every interested party appends a comment or recommendation on the document? Isn't this approach messy? Aren't there some cases where the updates get lost or overwritten? Not good enough. Or maybe in your organization you have a centralized repository where you maintain the specification document and all the interested parties can comment there. But still, are you able to maintain the older version of the same document? Say you have modified the document based on someone's suggestion, and after a few days it was decided that the previous design was better. Can you roll back to the previous design or the previous version of the document? Maybe, maybe not. And what happens when the centralized server maintaining the document goes down? Lot of issues. Wouldn't it be cool if you could implement this review process using blockchain and thereby solve the problems involved with the traditional approach? Two keywords: immutability, decentralization. We can achieve this using blockchain. So how do we do this? What will the transaction flow look like in this case? Let's have a look. Let's assume that an initial version of the specification document is available and a stakeholder, which is a registered user in the network, wishes to make a change in that specification document. Let's call him Gopal. So Gopal initiates a transaction which is a simple change in the specification document. So the client connects to a peer of its choice, let's call it peer A, and the transaction proposal is constructed. Proposal is basically a request to invoke the chain code function. Also, the user's private key is used to sign the transaction proposal to produce a unique signature. Second, the endorsing peers receive this particular transaction proposal that has been created, and the endorsing peers verify the signature to make sure that the client submitting the transaction proposal is indeed eligible for changing it, and there is no replay attack, as in same proposal has not been submitted in the past. Once the endorsing peers are satisfied with the proposal, they invoke the chain code function. Remember chain code, the business logic installed on every peer? Yeah, that's the one. So the chain code is executed against the current state database, and the result of the execution is signed by the private key of all the endorsers, and the proposal response is generated. In the third step, the application gathers all the responses from the endorsing peers and verifies the signature of the respective endorsers, and then compares the responses for all the endorsing peers, right? So basically the endorsement policy is defined by us. We can say whether n number of peers should endorse, or all the peers should endorse, or only one peer should endorse for a transaction to be marked as valid. Totally our choice. In our case, I'll be choosing two endorsers, say this one and this one, right, to mark our transaction as valid. And once they approve of our transaction, we are good to go. In the fourth step, the client assembles the transaction responses, right? Yeah, this one, the client, our very own Gopal, right? So, and sends it to the ordering service, because now the endorsers have verified and they are happy with it, with the change. So the orderer now comes into the picture. So orderer receives this response, and then now it is the orderer's responsibility to publish it, to broadcast it and ensure that all the connected peers receive it. So now the ball is in the orderer's court, right? Next, the orderer delivers the blocks of transaction to all the connected peers. If one thing to remember is that if the inflow of transaction is too high in the network, then updating the ledger for every single transaction would be too costly. We don't want to do that. So what happens is all the transactions are stacked in a block and n number of transactions are delivered in one shot. In our case, though, we don't expect too many changes, so maybe we'll implement it in such a way that every time some transaction transpires, we are going to update it in the blockchain, right? One more point to remember is that the ledger is updated with both valid as well as invalid transaction. So, whether a transaction has been successful and has been reflected into the current state database, or the transaction has been marked as invalid and ignored. We don't care. We are going to append everything. We are going to keep track of everything that has transpired on the network in our blockchain network, in our ledger, right? So along with this, along with the transaction block, we also have a flag marking that as valid or invalid, right? And sixth and the final step, each peer appends the block, each peer, when the orderer sends them, it appends the block to its own chain, and the chain code increases, the chain in the blockchain increases. And well, the client is finally informed whether the transaction was successful or unsuccessful. Very simple, right? In the next video, we will see the implementation details on how we can implement this simply, right? Also in the comment section below, I have mentioned some links where you can actually go through the Hyperledger documentation and you can start your own implementation, because there are tons of very, very simple examples. You just follow those steps and modify the chain code and change the scripts. It is very simple, trust me. So get going. See you next time.